Okay, so I'm Andrea Guerrieri, nice to meet you. So I just started in London as a lecturer 1 month ago, basically. And they asked me to give these lectures. But disclaimer, I was forbidden to basically teach what I work on. So maybe I will slip things through. It's like somehow it's forbidden, too complicated. I don't think so, but I think they're overestimating you. But anyway. So I decided to basically go for something maybe perhaps more useful in general. Okay? So the idea, well, first of all, the idea came from the fact that we are 52 years since the discovery of asymptotic freedom. So it's like 52 years of QCD. And in my opinion, QCD is like the most successful and beautiful theory that we have so far. And all other theories that you can imagine, like string theory, lattice gauge theory, anomalies concept, instantons, whatever, it all originated from QCD and try to understand the physics of strong interactions, so nucleons, pions, and all the stuff that make matter exist, right? So the fact that we exist is from QCD. So my first take on this is to ask you what is QCD, like what we mean by QCD. It's like a very general question, right? So, and today we know that a quantum field theory, it's not an abstract concept, it's energy flow, okay? So we think about QFT as energy flow from a CFT, conformal field theory in the UV, that goes once we turn on some parameters, which can be masses, can be coupling, and once we choose some kinematical quantities like number of flavors, number of color, can flow to some phase. Now, where do we flow depends on these parameters, how we turn it on, how we tune them. So, for instance, in the case of real-world QCD, we end up into a gapped phase. But you could very well tune the parameters and end up into some different thing, into a gapless phase, where the physics is described by massless Goldstone bosons. Or if you choose this parameter carefully, you can even end up into something even more weird, which is like a CFT in the infrared. Okay? On the other hand, this is not the only way to define QCD, because you can also start from a lattice gauge theory. So you can start from somewhere else, which means that you have a lattice model, you have some lattice gauge theory, and then you can flow to the IR and end up into some Euclidean theory, which again, if you tune carefully the parameter in this flow, it is related by analytic continuation to the Lorentzian gap theory, where you perform experiments. Okay, so we can explain the experiments here. So, what is QCD? It's a very broad question, right? It's all these things at the same time. Okay, and in particular, by tuning parameters, you can discuss a lot of wonderful physics of gap theories, and so on. But why it makes it hard? The fact that it's so hard to study all these theories is because, in general, the beta function of the coupling G is negative, and this is what was discovered 52 years ago. And this is what we call asymptotic freedom. Right? And asymptotic freedom tells us that the CFT in the UV is some beautiful free theory. So we are happy about the UV, but not so happy about the IR, because in the IR, since the beta function is negative, it will become strongly coupled. And in the IR, it's very hard to study all these things. So we have to come up with some techniques. So let's say the aim of these lectures, maybe not of the first one, which is basic review, but the broad aim of these lectures is to introduce two different techniques to study the fixed points of the RG flow, or maybe not fixed points, but okay, of the RG flow, which is the operator product expansion when we are close to the UV point, and the effective field theory techniques when we are close to the IR. Okay? So these are two effective descriptions that we use to explain other experimental data at low energy or at high energy. And this is, if you want, it's Weinberg chapter 19 and Weinberg chapter 20. So if you want to extrapolate from this broad picture, what I will talk about is about chapter 19, chapter 20 of Weinberg. That's it. But the physics is effective field theory operator product expansion. Okay, any question? Okay, so let me ask maybe, how many of you are familiar with these things in general? Am I being too basic, too, more or less? Okay, well, okay, because I'm going to start from the very beginning in the sense that, so in this first lecture, let me introduce what I want to do. In this first lecture, I want to review a tool that is very useful to study non-perturbative quantum field theories in general, which is the quantum effective action. So if it's something that many of you have seen already, or do you know about this quantum effective action? Okay, so it will be a review trying to explain the basic concepts. And then using the quantum effective action, we'll get like a proof of the Goldstone theorem, which is very fast. Okay, so will discuss about Goldstone, this gapless phase where steam is spontaneously broken. If there is time, I will explain also like some more different proof, which is not based on quantum effective action, but is based on some more general principle. Well, this is also general, but makes it more basic proof. And then in the last part, from this Goldstone theorem, I will discuss the pion sort theorem. And this is a little bit the start of what then is become the chiral effective Lagrangian or effective field theories. So I thought that would be a good idea to review some basics in the first lecture, and then in the next lecture we'll go like into more deep physical things. Okay? Okay. So let me remind you what we wanna do with when we have a quantum field theory. Okay? So in general, we like to define stuff like partition functions. When we have some, we imagine we have some quantum field theory, we source it in some way, and we write the partition function. But what is the partition function? It's a vacuum to vacuum transition, right? We have like the vacuum in the out state, and we compute the overlap with vacuum in the in state, in presence of some source G. And we learned from Tarek's first lecture that this object can be computed with a path integral, right? So d phi e to the I, and there will be an action, okay? For simplicity, I imagine that these fields are scalars, and I couple it with some external current. I'm sourcing the scalar field phi. Now, when someone writes an expression like this to you, you should always complain, because these objects are always infinite and make no sense. So when someone writes a partition function, you always complain. You should always like, what do you mean by this? Okay? So what I have in mind here, for instance, how I define this measure here, I really think it's like some product over all points in my space-time of d phi y. And I always have in mind that my space-time is some lattice. Okay? There is some lattice discretization. This is how I make sense of this expression. Now, when I write this scalar product, for simplicity, I write d for x, j of x, phi of x. Okay, so I will just write it like this. And then what does this partition function do? Well, this partition function is nice because if we take derivative with respect to j, we generate all correlation functions, right? So for instance, just to make a simple example, if I take delta and delta j of y of dz, the derivative will take down a field phi, and this will be the expectation value. So this will be the integral in d phi of phi at y with this action, and this will be just the expectation value of the field phi in presence of the source J. Now, let me still write it like this because it's not really an expectation value with some kind of probability distribution because it's not normalized. So this is not still a very nice object. In particular, when you expand perturbatively, this object will contain also disconnected diagrams, which makes the expansion very messy. So what you want to do in general is that you want to introduce, so let me start to erase things. So you want to introduce a free energy okay. So you want to introduce a free energy W, which is basically Z of J will be e to the I W of J. But is this too skewed, or I have to put it more vertical? Let's not touch, because I already touched it. I think it went a little bit down. It's fine. Okay. 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 So we introduce this object, and this object is nice because this generates all connected diagrams. In particular, for instance, at 4 point, this will generate stuff like this. All connected diagrams. And if we take derivatives of W, which is now the log of Z with respect to J, this will give us some nicer correlation functions because they are normalized with the vacuum transition. So it will give us stuff like vacuum in the out state, the operator phi, if this is at y, be phi at y, in the in state with the source J, normalized by the partition function. This operation is nice because in the perturbative expansion cancels all the disconnected diagrams. So we have all connected diagrams, which makes our life much easier. Okay? Now let me call this expectation value phi of y with a different letter. Let me call it like this. And now let me introduce the quantum effective action, which is mathematically, and then it will have like a very nice physical interpretation, but it's mathematically defined as the Legendre transform of the free energy. So we introduce this gamma minus gamma of phi, which is Legendre transform of the free energy, like this. Of course, now there are phi, j, there are too many variables in this equation. There is only one variable, because now we have to invert, and we have to express j as a function of phi using this equation. So you see, basically, phi is the expectation value of our fundamental field in presence of source j. Okay, and then tuning phi, basically, we can source it or we can see it in the other way around. It's a Legendre transform. Okay, so why we do this? Well, diagrammatically, I remind you that this is very nice because this is now generating only the one particle reducible vertices. So it will only generate stuff like, for instance, at 4 point, will only generate diagrams like this that cannot be cut by cutting one line. So in other words, the quantum effective action, if you are able to compute it, this in general is very hard, even in even in the Gaussian model, like it requires some work to do it. It generates right away all the vertices of the theory, all the fundamental vertices of the theory, which are the sum of all the diagrams here inside that cannot be split by cutting a line. Okay? So for this reason, it's a very fundamental object. Now, so let's look at some properties of this Legendre transform that will be useful later. So for instance, let's see what happens if we take derivative of gamma with respect to phi. Like what if we take the functional derivative with respect to phi, what do we get, right? So for instance, in this case, we just apply this formula. You see that you will get delta W in delta J, but J depends on phi, so you get delta J in d phi. Then from this term, we will get minus delta J in delta phi times phi minus J. But from definition, the derivative of W with respect to J is phi, so this is phi again. These two cancel, and then we see that there is this very nice involution that tells us that the derivative of gamma with respect to phi is again minus J. So now if we take again the Legendre transform of the same function, we go back to the free energy. Okay, so it's like a very nice operation, the Legendre function. And another nice thing of this relation that I write again, which is very important for the physical interpretation of this effective action, is that in absence of sources, when J is equal to 0, the stationary solutions, I mean the extremum of the quantum effective action, okay, are actually the configurations of the field in absence of source. Okay? And this we'll see that in a moment that this is connected actually to the vacuum of the theory. Okay, so this will help us to compute or to understand the properties of the vacuum of the theory. Okay. Now, before going, okay, so if you, like, there is some nice trick maybe that I learned by preparing these lectures that I never bothered to learn, but I think it's very nice, like to understand geometrically what it means, the Legendre transform. Okay, which gives you some intuition of why you write it like this. So basically, imagine that W, so let's do it geometrically. W is some convex functions, like this. And now, let's take one point here. So this is J, this is W. Let's take point J here. Let's draw the derivative, the slope. And the slope is phi, is what we define by phi. Okay. And then we will have some intercept. Sorry, let me do it in a way that is like nicer to draw. Okay, let me do like this. That's a bit nicer. Okay. And now I look at what is J times phi. So geometrically, J times phi is this side, and phi is the tangent of this angle. So basically, J times phi is this side of this triangle. But this side of this triangle, this is W, and this is what I define by minus gamma. And this is the Legendre transform. So basically, the idea of Legendre transform, it's very nice. It's like the idea of parameterizing a function, not as a function of the variable x, but as a function of the slope. And when the function is convex, this is one-to-one map. So you can really jump from one description to another. Okay? Because you see, for each value of the slope, I basically have one point on the curve. So that's why I can parameterize it using the Legendre transform. Okay? Okay, so this is like some nice property, geometric property. I don't know, have you ever seen this geometric property before? Okay, so maybe it's some of you was too basic. Okay. So one of the properties that one can prove in general, even from the picture, which is also nice, is that now if we take derivatives, so this is the property that we will use later. So if we take derivatives of the free energy, let's say with respect to two sources, and then I take derivatives of the effective action with respect to two fields, Then this is what we would say the dressed propagator. Right? Because it's just, you take two derivatives of the free energy and then you get the dressed propagator. And this object is delta, of course by definition, so using this definition, is delta phi with respect to delta j of x. And then instead, if we take two derivatives of the effective action with respect to two fields, what we get is, let's see, from the definition we get minus sign, and then we get delta j of x, if you want, in delta phi of y. So this tells you that if I call this object delta, in inverse notation, if I call this pi, x of y, then delta x of y to the minus 1 is equal to pi, minus pi. In other words, the one particularly reducible two-point diagram that comes out of the quantum effective action is the inverse of the propagator. And if you want to see it in terms of, like in more explicit terms, for instance, you can imagine that if you're like a propagator, normalized propagator, you get stuff like 1 plus q squared plus m squared minus self-energy minus I epsilon. And this self-energy is indeed the sum of all one particular reducible diagrams. So it really appears here. And this is just the three-level contribution. Okay? Okay, so this property is also nice because it tells you that somehow the curvature of one function is the inverse of the other function. It's some property of these things. Now let me do some explicit example. Let me try to compute this quantum effective action for some theory. Let's say for some scalar theory. How do we do it? So how do we compute it in practice? Yes. Yes. There is an I that I'm not tracking. You can always, you know, absorb it in the definition. Okay, so let's try to compute this object for, let's say, we have like a scalar theory, very simple, the usual 5 to the 4. So the action, there will be like some minus d for x, then we have lambda plus 1/2 m squared I squared plus g 4 factorial 5 to the 4 plus 1/2 d rho phi d rho phi. Okay. So, and well, since we can choose the source, we can choose for what value of the field we can compute it. Let's say we compute it for some configuration which phi is a constant. It's our choice. We can compute it for any choice of phi. But let's do it for the constant. And now the trick to, let's say, the way to compute it actually goes by a name which is called the background gauge. Sorry, not background gauge, background field method. It is a very useful trick. And the trick comes from this observation that from the definition, so from this definition, and from the definition of the free energy, we know that I to the IW, which is none other than gamma phi plus j times phi, is equal, this is the partition function, so is equal to the integral, functional integral d phi e to the I action plus source, like this. So now you see why it's called quantum effective action, because basically I exponentiate this thing and I get the same expression that here I just average over fields. So you can see that when fields sits on a classical configuration, the two objects are the same. From this expression is pretty much explicit. Okay. So Now let's do the following. So let's multiply by e to the minus ij dot phi here. So if we do this, we get this. So I want to basically make explicit this intuition that we basically compute just, well, we will get like the the usual loop expansion. So I multiply by e to the minus ij phi. So here on this side I have only gamma phi. I get this when I multiply. And now let me do a field redefinition. So let me change phi to phi plus phi. And then we get this very beautiful trick because we get action evaluated phi plus phi plus j dot phi. And this is equal to the e to the I effective action for our configuration phi.
And so far as wasn't important that
it's a constant. No, so far no. This is like the background field method in general. Now we'll specify to compute basically the effective potential. Okay. So this is very nice trick because now we can do the following. Now we can, for instance, imagine to evaluate this gamma on a extremal configuration. Okay, so an extremum. So let's say that delta gamma of delta phi is equal to 0. So that in particular means that the source is equal to 0. Okay, so we can also set this j equal to 0. Now, if we take this derivative, so let's do it. So if we take derivative of this expression with respect to phi, okay, on this side we get something proportional to gamma, which is equal to 0. So we have 0 equal integral with respect to phi, and here we get basically the derivative of the action with respect to phi with e to the I s. So this in particular implies that this derivative must be equal to 0, right? So requiring that requiring for a extremum solution of the quantum effective action, it's also like an extremum solution for the actual action of the theory, but of course like in average, like the expectation value. Okay. Now this delta s in delta phi, okay, I remind you that, well, we can also write it in this way. So I can shift phi plus phi. I derive in phi, which is linear, and I can get this relation, right? So this is telling you that when we expand around this solution, we are also expanding around if it were Euclidean, it would be a saddle point of this action. But in this case, we just use the stationary phase approximation, okay, and maybe I should do it here. So let me do it here. We want to use the stationary approximation of this expression. So what we would get? We would get e to the I gamma phi at the minimum times the integral in d phi, sorry, s. So I'm computing the right hand side. The action at the minimum in d phi, e to the I. Here there is second derivative of the action, computed at phi equals to well, phi plus phi equals to 0 times phi squared. I didn't shift. plus dot dot dot. Okay? And there is a factor 2. Right? And this is e to the I gamma. Well, it's the expansion of this function here, the gamma phi. Right? Now, for this expression, I mean, if we stop at 3 levels, so if we ignore the correction to do this integral, at 3 level, this tells you that basically gamma, the effective action at 3 level, it's just equal to the action evaluated in this phi minimum position. And now, so let me go here, let me erase this. And now we just can specify phi equals to constant, which is what we want to do at the beginning. Okay? And evaluate it. So we evaluate. And to get like the 3 level effective action, we just evaluate S on this constant configuration. So we just get lambda plus, well, minus lambda plus 1/2 m squared phi 0 squared. Sorry, let me be careful with the notation. So let me call this constant phi 0. This will be constant plus 1/2 m squared phi 0 squared plus g over phi factorial phi 0 to the 4. And then, okay, the derivative disappears. Times the integral in the 4x. Okay? This is barely divergent, and that's why I said at the beginning that this stuff, they always have lattice somewhere. So this object is divergent, and I call it just V4. And then the definition that I have here is that I can define the effective potential as a function of phi 0, which is just, well, sorry, let me do it in this way. So this is what I call gamma at 3 levels. So this is my gamma. And so the effective potential, it's just this part of the quantum effective action. So the effective potential, it's just gamma divided by this volume with the minus sign. By definition. So it's just this part. Okay. Now, what happens if you compute quantum corrections? Well, of course, this is just a classical potential, which is true if you are in a theory that perhaps, I mean, you are close to the UV, you have some weakly coupled flow, so you don't do much, and this approximation is more or less correct. But of course, this is in QCD, it's not what happens. This effective potential, as soon as you turn on loops, it becomes something that you cannot control. So there are not many examples where you can actually compute this effective potential. But in general, you see, by studying this object for this simple configuration of fields which are constant, tells you a lot about the vacuum of the theory. Now, let me try to... right. So are there any questions, by the way? Is it too fast, too basic? No. Huh? Okay. Okay. So there is one last step to understand like why we care about the minimum of this effective potential, right? Why do we care? And because there is like an interpretation of the quantum effective action, which I don't, well, I don't have time to do now, which is as like expectation value of the Hamiltonian. Okay? So in other words, when we minimize the effective potential, we are also minimizing the energy of the system in absence of sources. And that's why this gives a condition to find the vacuum. But of course, this object, it's very complicated to compute, unless it's tree level, where it's just this. Okay, so in general, it's a hard question to find the vacuum for this reason. But okay, if your theory is just described by this phi 0 to the 4 at tree level is enough for you the tree level, then you can just take derivatives of this function with respect to phi and find the minimum. Right? So for instance, like depending on the sign m square of this potential, you will get stuff like this, right? Which is the usual, well, it's like a nice vacuum here. Or if m square is negative, you can get stuff like this. And this, like, we will do it in a second. Okay, when you're like, well, like a non-trivial configuration where you have two values. And this is all tree level, by the way. So what you want to ask, for instance, is what happens at all loops in this case. And for instance, in this case, it's conjectured that all loops, this potential actually flattens here. And it goes like this. Okay? So it can be very different. Okay, so okay, so for now, so the take-home message. So let me try to summarize a couple of take-home messages from this section, because this is all I wanted to say. I just wanted to basically introduce this quantum effective action and explain how from this quantum effective action we can define an effective potential. And this effective potential is found just by looking at variation fields that are constant. Okay, and then when you minimize this effective potential, you can get an idea what is the vacuum of your theory. Then another important thing about this quantum effective action is that it generates only the vertices of the theories. So in particular, when in a second we'll do symmetry breaking, we will see that the symmetry breaking does not affect the vertices of the theory, but it just affects these vacuum solutions. So in particular, the original theory will always have the symmetry. Okay? So this will be the thing. So now let's go to what actually I want to talk about, which is spontaneous symmetry breaking. And before doing it, I want to ask, what is the policy with the breaks? Should we take a break now or in a moment? What? $40 minutes. Okay, so maybe I can okay, continue a little bit. Yeah. Okay, so let me continue a little bit. So now I want to talk about spontaneous symmetry breaking, because spontaneous symmetry breaking is basically almost omnipresent in QCD. And it's, well, it's basically what will allow us, probably in the next lectures, to write down the effective field theory for the low energy degree, which are the pions in this case. And to give you an example, which I like a lot of this spontaneous symmetry breaking, is, for instance, if you take the Young-Mills action, trace of f squared, okay, which naively at level, you might say the effective potential, it's just f equal to 0, but of course this is strongly coupled, so as soon as you turn on basically quantum correction, it will become very complicated. But there are solutions, let's say stable solutions of this action that admit a defect. So admit like a string-like configurations. And these are called flux tubes that are everywhere present. And such as a flux tube, it identifies a completely decoupled sector of Young-Mills. So in presence of a flux tube, two flux tubes, and so on, these are like super selection sectors. And in each of these sectors, the Poincare symmetry is spontaneously broken. Okay, so in this case, since you have this string, which is explicitly sitting somewhere, you can imagine that the usual Poincare group, this one, so we are in d dimensions, the usual Poincare group is broken to Lorentz on the defect times rotation around. So this is an example of symmetry breaking. And what do you get from this symmetry breaking? Well, one of the first things that you get is that vacuum is not unique, in the sense that here I'm breaking Poincare, so I can surely put wherever I want this string. And the equations, so the Young-Mills Lagrangian will know nothing about it, doesn't care where you put it. Okay, so there must be some consequence of this simple statement. And this is basically what spontaneously, theories with spontaneously broken symmetries do. Okay, they basically encode in a very nonlinear way these symmetries. Okay, but now let me start from some very simple example. So I want to prove the Goldstone theorem with using this effective action formalism. Because now, something that I don't have time to prove because it's a whole, it's a whole class basically, is that if you have a symmetry, so if we really have like a linearly realized symmetry, so phi n is equal to sum over n of some matrix phi m, so it's a linearly realized symmetry, then the effective action is invariant. Provided, of course, this symmetry is also symmetry of the action. Otherwise, it wouldn't be true. So if the action is invariant, it means that in particular, when we are at the minimum of the effective potential, and we have a solution, so this is like the solution of the minimum of the effective potential, and we apply the symmetry, and this is different from 0, then it means there will be like multiple vacua, because gamma takes the same value. So if it takes minimum at phi bar, we'll take minimum at L phi bar. Fine. So there will be what we call degeneracy of vacua. There are many, many vacua. Okay. And now let's try to understand what are the consequences of this. So to do so, we have to use what are called the Slavnov-Taylor identities. Okay. Which are very easy to prove. And do you know these Slavnov-Taylor identities? Okay, so they are very, yeah, they are used in the normalizing gauge theory. So they got the name because they are very useful. But they are very easy to prove, and it has like very nice consequences for the effective action. So basically they say that, well, when you compute the effective action, of course, so let me write it as like the integral in d phi e to the I s of phi plus j dot phi. And we perform a symmetry transformation, so we send phi to t dot phi, some matrix times phi. If the action is invariant, this of course is just the integral in d phi. So if the measure is invariant, it's the integral in d phi. If the action is invariant, this is just this thing. But what changes is the source term, of course. So this will be like t dot phi. Sorry, L, I called it L before, L dot phi. Now, if L is some continuous symmetry, so I can expand it around the, let's say, the identity for simplicity. So if L is something like 1 plus IT, okay, with some parameter epsilon plus dot dot dot, you see the magic, because now you can basically expand this exponential and get the same partition function as before when L is equal to 1, but then you get something which is like minus epsilon integral in the phi of j t phi. And this has to be equal to 0. Okay? Now, this in particular is what? Well, this is basically, so let's write it explicit, because here there are a lot of dots that are implicit. So explicitly, we are saying that the integral, let's say in d for x of source j of x, and here we have like some matrix, so the source will depend on n, there will be some n m, here I'm summing, and here I have d phi, phi m, e to the I s of phi plus I j phi. Okay, but this is what? This is just, well, this is just the expectation value in presence of source of the field phi m. And this has to be equal to 0. So in particular, this is telling us that if we go into the effective action language now, this is telling us that the trace, basically, so the sum over n and m of this integral, t for x, jn, well, jn of x is the derivative of the effective action, so delta gamma of phi with respect to delta j n x times this matrix times phi m. This has to be equal to 0. Okay, so these are what are called the Slavnov-Taylor identities. And now these identities have consequences for the effective potential.
How did you go from the expectation function to the effective action?
Ah, yes. So by definition, I remind you that the expectation value of the field phi with source j is phi. Right. And then the current j is the derivative of the effective action with respect to phi. Sorry, here there is like phi, and that's it. Now let's take again, we take phi equals to constant. It's like a simple choice that we like. And if we take phi equals to constant, then this thing reduces to the effective potential, right? So this just become derivatives and not functional derivatives. So it just become a condition of the form, just to not mistake the notation, dv in the phi n times phi n. Because this is now fixed configuration, so I don't have to integrate. Okay, and this has to be equal to 0. And now we can take derivatives of this expression. So if we take derivatives with respect to, let's say, phi l of this expression, what do we get? So we get sum over n and m of dv d phi n times tnm phi m plus sum over n and m dv d phi n t n l equal to 0. But now let's sit on the minimum. So let's sit at phi equals constant equals to phi bar. So the minimum of the potential. And then this can be set to 0. And then what we get is this relation. That, so let me erase here. You see, we get this nice relation that the sum over n and m of the 2b in the phi n, the phi m, phi l, sorry. Then we have like t and m phi m is equal to 0. Now, what does this mean? Well, I remind you that again, effective potential, it's just, it's obtained from the effective action. And if I take derivative with respect to effective action, I get the 1 pi propagator. Well, the inverse of the 1 pi propagator. Sorry, the inverse of the connected propagator is this thing. So this can be written as, so this of course for phi equals phi bar at the minimum, but you write it here. So this is called mass matrix in general. And this can really be taught as the inverse of the propagator with indices and NL, and at 0 momentum because we are computing it at the vacuum and for a constant configuration. So it's really at 0 momentum. TNL, phi bar equal to 0. But now the symmetry breaking argument enters because now this sum is different from 0 because the vacuum is not invariant. Therefore, this new phi bar prime of n is an eigenvector of the mass matrix with eigenvalue equal to 0. So it tells in particular that delta, the propagator, NL of Q should behave like 1 over Q squared. Okay? And is it clear? Sorry? Ah, yeah, sure. So I'm saying that this object here, okay, it's basically the inverse of the propagator. And now I'm saying that because of the broken symmetry, when I rotate the vacuum phi bar with t, in the matrix T, I get a non-zero value, which is like some phi bar prime. And therefore, this is like an eigenvalue equation. So now it means that this operator here, which is like basically the mass matrix, will have an eigenvalue 0. And these guys here are the eigenvectors. So in particular, if there is like some A, so if this group has some rank, which this A labels the broken generators, there will be like 1 0 eigenvalue for each broken generator. And this is give you some very, let's say, straightforward proof of the Goldstone theorem.
Basically, it's the same that there are 0 masses.
Yeah. Yeah.
And there are infinite quarks to derivative them. The propagator is 1.
Yeah. Exactly. Okay. So now there is like a very simple example. Then maybe we can have a break. So let me do some computation, which is again the same potential that we had before. So let's do a simple example. Let's take this Lagrangian and let's see this explicitly. So we have this Lagrangian minus 1/2 with a bunch of scalar fields, and then let me write square divided by 2. This is phi square, where phi square for me is this expression. Sum over n phi n phi n. minus g 4 factorial phi to the 4. Sorry, phi square, let me call it phi square, okay? And of course, the effective potential, it's just this part. So this is just minus the effective potential, this part here, at 3 level, of course. Okay. So then, well, we take derivative, of course, let's imagine that m square is negative, which is the interesting case. So let's take that m square is negative. Then we take the derivative, and let's see, we get something like of this thing. So we get m squared divided by 2, then we get 2 phi l plus g, is like a factor, they do 4 or 4, no, the 4, it's better. So there's a 4, and then I take 2 times this phi squared, and then I get 2 times phi l equal to 0. Okay, just take the derivative of the effective potential. Okay, and this equation tells us right away that, so this cancel with this cancel with this, and it tells us that phi squared should be equal to minus, so phi squared should be equal to minus m squared divided by g. Okay, and this is the usual, so it's the potential that I drew before. Okay, so this is basic, but now let's compute the mass matrix in this case. So let's see explicitly that we have these gallstones. So if we compute the mass matrix, we need to take one more derivative. So we have to take one more derivative of this expression. Yes, so if I take one more derivative, I get m squared. So this is like, let's call it mass matrix. We should be, so from this I get delta, if I take the derivatives. So it will be m squared delta mn. And for this guy, from this guy, I get plus 2 times g phi n phi m, and then there is like plus g, take derivative with respect to this, and I get phi squared delta n m. And now, if we evaluate this on the vacuum solution, for which phi square is equal to this thing, these two terms cancel, and the mass matrix is just 2g phi n phi n. Where this is like phi bar, is this phi bar. And now, what is the rank of this matrix? So it's matrix 1. Good. Because it's matrix which is the outer product of one vector. Right? So it's like not very, right? There are not many things to do. So it has rank 1. So in particular, if we compute the trace of this mass matrix, we get 2 times g phi bar square, which is basically just 2 times absolute value of m squared. Okay, this is the only eigenvalue which is different from 0. All the other eigenvalues are equal to 0. So we are in this example, since we have, maybe I didn't say it, but the small label n, for me it means 1 to big N, is what it means. So here we have like one eigenvalue which is different from 0, and n minus 1, which are equal to 0. And this is the number of Goldstone bosons in this model. And then you can check this formula in this case, because this corresponds naively to the breaking of some rotation symmetry On into On minus 1. And then you can check naively now by counting. So let's do the counting, that if I do n divided by 2 times n minus 1, right? So antisymmetric matrices of n by n, antisymmetric matrices, minus n minus 1 divided by 2 times n minus 2, okay? This is just, so this is like the rank of On. This is the rank of On minus 1. This just gives n minus 1 divided by 2 times n minus n plus 2, which is equal to n minus 1. So it checks the number of Goldstone bosons. So you see, we broke On into On minus 1, and the number of Goldstone bosons correspond to the number of generators that have been broken. Okay, because the rank between these two groups differs n minus 1. Okay? Okay, so I will stop here, and maybe we can get a coffee. Okay. Now I have to decide what to do. And the question is, how many of you have seen already like the proof of the Goldstone theorem based on current algebra? No, okay. Huh? No, no, no worries. No, because I tell you why I'm asking this. Because for instance, in Italy, when I did the master, this was something that was like in the QFT basically class. Huh? Right. I will not really go into the details, but you know, using currents, commutators, all these kind of things, let's say. So it was something that we studied at school, let's say, and to me it looks like something basic, but I mean, if you've never seen it, maybe it's a nice idea, because it's a nice idea to do it. Because the techniques that you use to do that basically are a little bit bootstrappy, in the sense that you use spectral functions and Lorentz invariants. So this effective action formalism will be useful in the next lecture, when I will try maybe also to make contact with some modern techniques that people use to compute chiral perturbation theories or to do actual computation, low energy QCD. But this other proof instead, it's like maybe more elegant, although like it's a little bit more technical, but it's like more nice conceptually, because introduce spectral functions and yeah, and all these concepts that usually are actually what I work with every day. So, okay. But can I restart now? Yeah. Okay. Okay, so now let's try to prove it. So again, with some basic, using some basic facts. So if we have a continuous symmetry, right, then we all know that Nether theorem, so Nether theorem tells us that there exists a current which is conserved. And so far, I'm not saying anything crazy. So there's like a current which is conserved. Now, when you have a current, you can construct a charge, of course, by taking the zero component and integrating over the volume of space. So d3x, j0, xt. This can be done for any t, okay, because the charge is a conserved quantity, and therefore whatever t I choose is the same value. And the charge is what generates the transformation of fields. So the charge, when I apply it to a scalar field phi n of x, it generates its rotation. So it rotates it infinitesimally by Tnm phi n of x. Okay, so now we want to basically prove the Goldstone theorem, And we want to start from some very specific commutator. So let's start from the commutator of the current at y with the scalar function phi n of x like this. And let me do some non-trivial step that I will justify in a second, which is that I can write this current, this commutator, as I over 2 pi cube. Then I can write it as d for pi, d for p. And then I have some functions, which are the spectral densities, minus rho 3 by n lambda of p. Okay. Ah, sorry. Oh. Sorry, there is like some phase, of course. There is e to the p y minus x. Then there is this thing. Okay. So how do I get this this expression? So let's do it. So let's start from the simple or like one simple ordering. So I just take j lambda y phi n of x. Let me insert a complete basis of states. So I insert n in a sum over n. Let me use translation invariance. So let me basically use the fact that I can put this operator at the origin, this operator at the origin, and the price to pay is the price to pay is that I pick a phase. So I pick e to the pn y minus x. And now let me write this as an integral in d for p, and here e to the p y minus x, and here I have this sum. So I have like sum over n delta 4 of p minus pn vacuum current state n scalar vacuum. Just a chain of identities. And now let me call this sum 1 over 2 pi cube with an I rho and lambda of p. So this is, I just called it like this, and that's why it appears here. Delta function, the usual trick. So there is a delta function that appears inside, then you put an integral outside, and then you change name to variables. Some pn, I call it p, some pn, I keep them pn. Okay? So this I call rho and lambda, and now this rho and lambda, we use Lorentz invariance. It's a function of p, right, of this external momentum, because we have a sum over n, so it's integrated over. So it can only be a function of p lambda. It can only be, I over 2 pi cube. Let me keep it for some aesthetic reason. So there will just p lambda, because it's vector. Then there will be a theta function. Why? Because we sum over physical states that have positive energies. And then there will be a scalar function rho, which depends on, well, which scalar I'm using here, and which I have minus p squared. And this is just because of Lorentz invariance. Okay, like there is an index lambda can only be taken by a p lambda. There is a Heaviside step function because I only have sum over states with positive energies, and then what remains is scalar function of p square, which is the only Lorentz invariant that I can construct with momentum p. Nothing else to do. Okay? And if I do the same for the other ordering, so phi n j lambda, this is how I get rho twiddle here. So you see, I took one ordering and I got rho and lambda p a phase. Then I take the other ordering, I get the opposite phase, and then I get another function, rho twiddle. Okay, now let me do another step, which is that, now let me take this function, d4p e to the I p dot y minus x I over 2 pi cube, and let me write explicitly. So let me write p lambda theta p0 rho n of minus pi square. And let me introduce another integral. So let me introduce the integral from 0 to infinity in the mu square of the delta p square plus mu square, which is 1. Okay? So now let me exchange the two integrals. So if I exchange the two integrals, what I get is the following. 2 pi cube, so I put 0, infinity, in the mu square here outside. Minus p square is equal to mu square, so I can put the spectral density rho n outside. The derivative, well, the p lambda, I can write it as a derivative with respect to y, okay? So I even put d in the y lambda, okay? So this is to take care of this. And I think this takes care of this I, that's why it's here. And then I put on this side all the rest. So I put d4p e to the I p y minus x. Then there is a theta, positive energy, and then there is a delta, p square plus mu square. Okay. Now, this is a known function, okay, that appears basically in a scalar theory. It's just a commutator. And in particular, this function, which is like, goes by name of delta plus, y minus x and mu square. This function delta plus, if you compute it in the Euclidean, it has just a simple expression, which is m divided by 4 pi square root of 1 minus x squared. Right? And then there is k1, which is a Bessel k1, m square root of 1 minus x squared. So it's just like an exponentially decaying function, some Bessel function. So this you can compute it, you know it explicitly in the Euclidean. It's an even function also in the Euclidean signature. Okay, so again, now I want to use this trick, so I want to use this, this identity. Okay, so I want to use it. I want to plug it inside this expression. So let me do this algebraic jump. And let me write again that the commutator of j lambda y I have x in the vacuum is equal to the integral 0 infinity in the mu square, and then there is just rho n, well, there is like a derivative, sorry, it's like equal to the derivative with respect to y in lambda, which is this derivative here, right? Rho n mu square times delta plus x minus y mu square minus or plus rho twiddle n of mu square times delta plus y minus x mu square. Okay, this is just by various redefinitions. So it became very simple, right? It's just some spectral function, some other spectral function for different ordering of these operators, and some non-function. It became very simple, this expression. The knowledge on the details of this operator J and phi, it's only encoded in this row. All the rest, it's very universal, because it's like a two-point function, so it cannot be much different than this. And now let me use some fact, which is that you know that a commutator, if I compute it at space-like separations, it should vanish. Okay? So a commutator, so when I take x minus y space-like, which I think in my notation is positive, in norm, what I get is that this is 0 is equal to the derivative respect to y lambda of the integral with respect to d mu square. And then I use also the fact that delta plus, which is a function that I know, it's known, it's even under change here. So it's an even function, therefore here I only get the sum rho n mu square plus rho twiddle n mu square times delta. Okay? Okay, and now, well, this is simple, right? This is a function that it's, well, some Bessel function. If I take a derivative, doesn't have any particular properties, so the only way for this integral to vanish is because this sum has to vanish. So one condition that we get from this, from the fact that commutators vanish space-like is that these two spectral functions are related by this equation. So this sum must be equal to 0. It's like some simple condition. Okay. But of course, for general x and y, this does not vanish. But with this condition, we get some simplification here, because now this expression here is equal to the integral in d mu square. I can use only rho. I don't need rho twiddle because it's related. So I only have rho. And then here I have d in dy lambda acting on the sum of delta plus with y minus x plus, no, minus, yes, x minus y. And this is not equal to 0, of course, in general. And it's not even when you are at time-like or light-like separations. This becomes the Feynman propagator when you dress it with the proper ordering, right? So with the proper time ordering, with the thetas, it becomes a Feynman propagator, exactly. Yeah, I don't know what is exactly the name. Weinberg called it delta plus. It's, you know, the basic block.
No, I mean the y minus x
But you need to put the temporal ordering, otherwise it doesn't become the Feynman propaganda. It's almost. Okay, so now we are almost done because now we have to use conservation of current. So we use the Nether theorem that this current is conserved. So we have to take derivative with respect to lambda. So if we take derivative with respect to lambda, this side vanishes, and there are no theta functions. So it's really the derivative acts on current. So this vanishes, and on the other side we get the integral in the mu square of rho n mu square, and here we have like box y acting on this difference. And now we use another property of this delta plus, which I remind you, this delta plus also satisfies this equation, that the Klein-Gordon equation, that this thing times delta plus of y minus x mu square is equal to 0. So we can substitute this operator here with mu square and then we have like delta plus minus delta plus with these two different ordering. And this has to be equal to 0. And therefore, we conclude what? Well, not yet, we don't conclude yet, but we almost got. So let me erase this first part. So using conservation and the fact that commutator vanish when you go space-like, we almost got that mu square, well, we got the mu square rho times mu square has to be equal to 0. But now, does this implies that mu square is equal to 0, that rho is equal to 0? Right? Because of course, like to say that we have states with 0 mass, we need the support of the spectral function rho, which is this integral of all the invariant masses, go to 0. Because if there was, because you see the spectrum, right? I remind you, the spectrum, if there is like a mass gap, so if this is like P0 and this is like P, it's like hyperbolous, where this is the one particle state and here there is the continuum. So of course, if the particle have masses, this integral over mu square doesn't really go all the way down to 0. Okay, so there is like no mu square equal to 0, of course. So mu square equal to 0, it tells that there is some particle with mass equal to 0, which is massless. But we have to exclude the possibility that rho mu square is also identically equal to 0. So this is the step to exclude. Okay, so why we can do this? Well, now we have to use right, some properties. Now we have to use the fact that symmetry is broken somewhere. So now we have to use the fact that let's set in that expression star, let's set lambda equal to 0, and let's take x0 equals y0 equals to t. So at identical times. Right, so let's consider this commutator now, J0, YT, phi n, xt on the vacuum. And this from all our formulas. Okay, what is this guy? So this will be, let's see if I can simplify a little bit. the integral from 0 to infinity in the mu square. Then there will be a rho n mu square. So I'm basically writing this formula at the end of the day. I'm basically writing this formula. Where now we have like equal time, so this exponential only knows the 3 momenta. Okay. Sorry, I should simplify it a little bit because I was doing it from the beginning again. One second. 1, 2. Okay. Square. Right. Okay, so I have this phase, then I have this delta p square plus, it's the formula that I just erased. I mean, okay, sorry. If I read it from here, would have been faster. So delta p square plus mu square, there was this theta. Okay, there was like a divided 2 pi cube, there was an I, which, okay, if I want the formulas correct, I have to put them. And then there is an energy, of course, which is like p square plus mu square.
No, but basically, what we can do is because all this is something proportional to n. Now, if n is 0, it's 0. But if you compute from commutator, what is next? It is 0. So, which proves that n cannot be identical to 0. And that's it, right? So
Yeah, basically that's what I want to do.
okay.
Yeah. So yeah, okay. So yeah, somehow what I was doing here. Ah, yes. Mm, 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 mm. Yeah. Uh, there is now I remember what is the step here because so what I want to do is the following. I want to use this property, right? As you said. So I want to integrate in d3y this commutator. Right, to get the charge. Right. And the only thing that, so, okay, so let me do the first side, then I tell you why I wanted to do this. So the first side, of course, this gives you this, then it gives the charge, the integral, then it gives this. And it is, of course, this commutator tells that this is just like minus sum over m, t and m, this expectation value. And this is different from 0, so of course the symmetry is broken. And now, what I wanted to say with this computation, it's just that this is also equal to I integral in the mu square of rho n mu square. Right, that's it. So basically from here I wanted, so let me just write the final expression, then maybe you can try to derive it as an exercise because it's basically using all these formulas. But the only thing I wanted to write about this commutator, I wanted to show explicitly that this is really equal to delta 3 x minus y, so that is delta function, times integral in the mu square rho n mu square. That's it. So this is just follows from these steps. I mean, I just have to, if I do it again, I get it. But now I wanted to simplify it and I could. Okay. So this tells you basically that this is different from 0, and therefore the only option is that mu square is equal to 0. And this is what tells us that in this spectrum there exist particles with zero mass. Okay. Okay. So this is um, and this is the content of the Goldstone theorem that we wanted to prove. So in particular, rho will be. We can also do some more computation and show that rho is actually proportional to delta of mu squared, because something that you have to show is also that this state is also isolated, right? Because there can be also the fact that you have like this function of mu squared. There could be a continuum of states if there is no gap in the spectrum, right? Because if now the mass square is equal to 0, you can have a gap at 4m squared because of the two particle states. But if m squared is equal to 0, everything collapses. Okay, so actually this density can like support like this. But this not happens. Rho is really proportional to delta mu squared. Yeah, every part, I mean, I only proven that this commutator couples only to the Goldstones. But this is exactly what I wanted to prove, that this is the commutator that is sensitive to the Goldstone. That in this sum, so well, that I don't have anymore, the sum over all the internal states, right? When I write J lambda n and phi, right? This is a single particle Goldstone state, right? Because the currents create Goldstone. So where? Sorry? This commutator. Only for space-like separations, but that's microcausality. So for space-like separations, this commutator has to be equal to 0. But for time-like separations, so when I can correlate stuff, it's not 0 anymore. And it's given by this average sum of the spectral function.
So have you only used the fact that it's the golden rule just there? That's the only place you actually use the fact that the golden.
Yeah, no, this is so this is general so far.
Yeah.
So this is total general. So this equation is general for conserved currents, right? Because we have to use the fact that the current is conserved, we have to use microcausality, and then we get this expression that mu squared times the density is equal to 0, right? But then the question is exact, that we have to show that rho cannot be equal to 0, and this is true only if, well, the expectation value on the vacuum of this field phi is different from 0. It's like non-trivial meaning. Exactly. Right. And actually, this like gives you some, let's say,
But this is what you should say. So we have this equation, mu squared rho equals 0.
yeah.
So the only solution is rho proportional to delta function. Right? There is no any other solution.
Well, rho could be 0.
Yeah, coefficient of the function 0, then
Yeah.
The delta function is very coefficient. And that's it.
Yeah.
So what shall we show with this continuum collapsing?
Ah, no, no, this is something more. Let's say this is something more. What I wanted to say is that that in this density rho, there is no such, well, you say that there cannot be, obviously. Okay, yeah, right. Yeah. So yeah, it's proportional. It's like a proportional to a delta of u squared. That's the simple thing that one can simply show. Now, what I wanted to mention now, it's some fact about mm, that one can derive from this Goldstone theorem, which is like the soft theorems. And soft theorems usually are very useful, are a very useful consequence, especially when you consider scattering amplitudes, because it gives you a lot of constraints. And also when you have like correlators in general. And it's the first example of nonlinear relation. Well, now it will be linear because it's just a zero, but in general, the soft theorems are like one of the many consequences of the nonlinearly realized symmetry that you have in this system once you break the symmetry spontaneously. And that's what I want to discuss in the next lecture. But now today, the only where I want to stop is that I want to just prove the what is called the pion soft theorem. Okay, just using this property here. Okay. So maybe, okay, I'll leave it there. Okay. So we might say that these are constraints on the possible interaction when you have this ghost. So what I want to consider now is this function where I have some generic state beta, then I insert the current mu of x associated to some broken generator, and then I have a state alpha. Okay. This, of course, I can write it as e to the iq dot x beta j mu in 0 alpha, where q is equal to p mu alpha minus p mu beta. And what I mean by alpha, so by alpha I really mean that there is some scattering state, let's say, or some correlation function. And then here in the out state I have some beta, this is some alpha, and there is some insertion of a current here, J mu. Then momentum conservation fixes this momentum Q here to be the difference between the sum of the momenta in the alpha state P alpha and the sum of momenta in the beta state beta, P beta. Okay? Now, the rules of polology, which is something closer to me, tells you that when let's say that when this current couples to one of these states, so there is like a non-vanishing coupling between these states, then this correlation function develops a pole, right? This also goes to name of factorization, right? So if this coupled to some internal line, you can always factorize this thing. So in particular, maybe let me write it and then we can comment. In particular, I can write this object, this transition, as I f q mu divided by q square times some amplitude here, which is actually the amplitude, the scattering amplitude for beta to alpha. So I'm really just factorizing. And why there is a massless pole? Well, we just proven that we have Goldstone bosons. this current coupled to a Goldstone boson, therefore it's like 1 over q squared. Now, let me be more precise, so let me write it a little bit better. So let me try a little bit more precise. So let me write this matrix element as a regular part, so there will be some regular piece that does not have a pole, plus a pole contribution. So it is clear again why there is like q mu here, because there is the only momentum. Okay, this function just depends on this momentum q, so there can be only like q mu, and then there is the pole, to the fact that we have massless particles in this correlation function, because the current couples to Goldstones. So this is like just Lorentz invariance, and then F is some strength of this interaction. And now let me use the fact that the current is conserved. So let me do d mu j mu on this state. And this is in momentum, well, in momentum space, this just gives me 0 equal to q mu and mu beta alpha plus I f q squared divided by q squared and beta alpha. And this has to be equal to 0. So this implies in particular that m beta alpha, so the scattering amplitude without the Goldstone, it has to be equal to I q mu and mu, sorry, q mu and mu beta alpha divided by f. And now, if we send q to 0, okay, which means that if we take this Goldstone and we make it soft, then this amplitude has to go to 0. Okay, so it vanishes. Okay, and this is what is called the Adler zero also. So this is what the Adler zero. Now, let me make a, we're almost done. So let me make a comment on this Adler zero, because I'm implicitly also using some fact. So I'm also implicitly using something else in this argument, which is the fact that I only told you that this amplitude is given by some regular piece plus a piece where the current is attached to some internal line, and therefore I can factorize on this pole. But in general, why I cannot have something like this? When you have like some state, beta, sorry, alpha, and here I couple, let's say, the Goldstone to the external line here, or I couple it here. Right? I can also have this kind of interaction. Now, if I have this kind of interaction, what happens? It happens that, let's say here, so this is Q, let's say, this is some momentum P. So here we'll have some propagator, which is like, this is P minus Q. So it would be like P minus Q squared. Did I put mass? Plus M squared. in general, if this particle is not a Goldstone, let's say. And this is, of course, equal to what? This is equal to q squared is equal to 0, so I have like minus 2p dot q plus p squared plus m squared. Sorry, no, this is like a current, sorry, plus q squared. Now, p squared plus m squared, this vanishes because it's like the momentum conservation. Therefore, this propagator is 1 minus 2p dot q plus q squared. And when q goes to 0, this goes to minus 1 over 2p dot q. And now what happens? Well, if I forgot to add this piece to this function here, then this function here, when multiplied by q mu, would go to a constant, right? So I would have like a constant contribution here that I'm forgetting. Okay? Okay. So this, like, we have to be careful because when we make this argument, we have to specify what is the trilinear coupling between the external particle and the Goldstone. And in general, these soft theorems can receive corrections. This is what happens if, for instance, the external lines are related to non-broken generators, let's say.
On the impression that a model is ultraviolet, right? Otherwise, you just push like scattering for any particle.
No, well, any particle in the theory, of course, on this theory. I mean, all these scalars. So there will be like a phi n scalars. There will be some that are related to broken generators and become Goldstones, and other that are massive, let's say.
And then it has sort of for every particle theory, this m of the beta will be.
Well, I said that I said this goes to 0 because I basically only thought that the only contribution that gives me a pole is when the Goldstone attaches to an internal line.
Yeah, but also when it disappears in your, I mean, you just consider matrix element, so you put everything, right?
Yeah, no, of course. No, yeah, no, of course. I mean, I have to do this. I have to add also these diagrams. Of course, I'm saying that usually in this proof of the Goldstone, one can be fast, saying that this thing attached to an internal line, picks pole, and then I neglect everything else. That's the only thing. But the important point here is that when you have Goldstones, you cannot have this interaction. And this is maybe the important piece that one has to add to this story to prove it, right? That you cannot have this interaction. Now, this will be obvious, I think, from the effective field theory, when you write down the effective field theory. But as a final comment, just say that this can also be derived from the quantum effective action formalism, because if you take, because you see, from this Legendre that you wrote before, was J phi, right? From this Legendre, we took two derivatives and it gave some relation between the propagator and the amputated propagator. But then if you take three derivatives, four derivatives, and so on, you get infinite relations that when the vacuum is non-invariant under the symmetry are non-trivial. And these are basically the origin of the soft theorems, that you have all these infinite relations between vertex functions. And the second one, beyond the, let's say, the 2-point function, is the 3-point function. So if we go back to the effective potential, and we take, instead of two derivatives that we used to derive the existence of Goldstone, we take three derivatives, then what you would get is some condition like this, d3v of this effective potential with respect to d phi, d phi, d phi. And this can be when you basically, when you multiply this by phi's, And when we sum, so there is some sum to make, this is equal to 0. And basically, since this object is equal to 0, it's telling you that you don't have three linear couplings between Goldstones. That's it. And therefore, this cannot happen if the external legs are also Goldstone, and therefore you get soft theorem, but only for amplitudes involving Goldstones. So if in a theory we have not just Goldstones, but we have also there's some other particles, let's say massive scalars, then mixed amplitudes will not have this property in general. That's the only thing. And I will stop here. I think it's, yeah, I think it's, yeah, please. Sorry, which property? Ah, I mean, so the physical meaning is that, the, I mean, I'm saying there are physical consequences that you can derive from this statement, because this is the basic statement. Then the physical consequences is that, for instance, derivatives, the interactions are derivative, right? Are derivatively coupled, right? Because interaction, they have like derivative of some field, because they have to vanish when the momenta becomes soft. And derivative interactions, for instance, tells you that when you consider scattering of these Goldstones in 4 dimensions, where you would worry about infrared divergences, like in gravity or in electromagnetism, you have like, you know, electrons, gravitons, you scatter, you get higher divergences. Goldstone amplitudes are totally infrared safe because of this property, for instance. And another thing is that these zeros are what you experimentally observe, and is what experimentally tells you that there is some symmetry breaking. So let's say if, you know, in a world in which QCD is gapless, there are really these massless particles around, then from looking at these soft theorems, you could understand, let's say, what is actually the symmetry breaking pattern. Right? Because which amplitude goes to 0 with which quantum numbers depends on the symmetry breaking pattern, right? Which can be very complicated. So it's really, it has a lot of physical consequences in the context of basic experiments, let's say.